we present Phi SFT, a new shape from template approach, SFT for short, with a physics-based deformation model. Phi SFT is an optimization-based method to reconstruct a temporally coherent sequence of 3D shapes from a monocular RGB video given a single initial 3D template in advance. Our deformation model is based on a physics simulation that explicitly accounts for the physical fold formation process and ensures high physical fidelity and realism for the surface evolution. Due to the differentiable physics simulator, the deformation parameters of our method are physically meaningful. We optimize these parameters via differentiable rendering by minimizing a dense per pixel photometric energy. Compared to existing methods, our 3D reconstructions of challenging surfaces are significantly more accurate and physically plausible. Our method models deformations as a response of the elastic surface to the external and internal forces acting on it. The internal forces are influenced by the elastic properties of the material, namely material density, stretching stiffness, and bending stiffness. We also model external forces, such as wind and corrective forces. Our framework assumes that a 3D template at the rest state is given along with the input image sequence. The physics simulator generates deformed future states of the template, which we treat as reconstructed surfaces. We now have a physical deformation model that is parameterized by a set phi of parameters and that outputs a 3D mesh for each time step. Our goal is to obtain a deforming surface from a monocular RGB video. As is common for many SFT methods, we assume that segmentation masks, camera intrinsics, and a texture map of the observed surface are available. We use a differentiable renderer to render the reconstructed 3D surfaces into images. In contrast to earlier photometric terms used for SFT, this allows us to define a reprojection error not just per vertex, but densely per pixel. We can thus exploit the information present in the texture regardless of the mesh resolution. We solve for the optimal physical parameters by minimizing the reprojection error between the rendered images and the input images. We backpropagate through the differentiable rendering and differentiable physics simulator to obtain the optimal set phi of physics parameters. The physics simulator acts as a regularizer during the optimization of our objective function. We evaluate our method on the new Phi SFT dataset containing 9 sequences recording with an RGBD camera. Please note that we use the depth channel for evaluation purposes only. Phi SFT reconstructs challenging surface deformations well by capturing both the coarse shape and local folds. We show depth maps reconstructed by Phi SFT. They allow us to visualize even more minor surface details, and we can see that they are captured well by our reconstructions. We compare with previous shape from template and non-rigid structure from motion methods. Phi SFT is significantly and consistently more accurate than related methods and supports finer scale local folds. This is because our method is aware of the physical fold formation process. In contrast, existing methods rely on simple geometric prior assumptions, such as isometry, and can only reconstruct predominantly global deformations. They cannot cope with the elaborate and challenging local fold patterns present in our new dataset. Finally, we present several ablation results of the proposed components. Our simulator does not describe hand contacts and wind turbulence, for example. Thus, naively using it leads to significant reconstruction errors. We hence correct these model insufficiencies by introducing per-vertex corrective forces that can vary over time. As we can see, they greatly improve the reconstruction quality. Note that the correctives could, in principle, account for any physical force. This raises the question of whether we even need the rest of the physics simulation. When removing all forces from the model except for the correctives, the results degrade in quality significantly, demonstrating the necessity for the physical simulation based on the internal stretching and bending forces. Since physics simulation is a temporal process, the early frames directly influence the reconstructions of the later frames. In addition, later frames are initially reconstructed at lower fidelity than the earlier ones. To account for these effects, we employ an adaptive training strategy where we grow the temporal window of frames actively used in the optimization. This scheme allocates more iterations to frames with more challenging deformations and exploits the temporal frame order for better convergence. Thank you for watching.